He's also a faculty research fellow at NTER. Saul got his PhD at Columbia in the Sustainable Development Program, which had produced one after the other undergraduate graduates, and that was after getting a double degree at MIT in atmospheric sciences and urban studies and planning. Before going to Berkeley, Saul made a brief stopover for a year here as a postdoctoral fellow in the STEP program, working in my research group, and we were lucky to have him, and sorry that he decided to leave to get a real job. Saul's a pioneer in using empirical data on responses to past climate variations to infer and quantify potentially new responses to future climate change. In 2013, Saul won the inaugural AGU Science for Solutions Award for the policy relevance of his groundbreaking work. He's probably best known for his analyses linking climate variability and change to changes in levels of interpersonal and intergroup violence. Work that's been controversial, to say the least, but it's a battle that Saul's winning. He continues to define the cutting edge of this field, and today will talk to us about yet another aspect of human responses to climate variability and change. And the title of this talk is, Does the Environment Still Matter? Daily Temperature and Income in the United States. Saul.
Thank you, Michael. Thank you for having me. It's great to be back. I should say at the onset that this is joint work with Tatiana Deryugina, who's at Urbana-Champaign. So the starting point here for thinking about what the question is, sort of why we titled it this way, is you can think about one narrative of economic history for humanity to be a gradual decoupling of our economic well-being from sort of the random stochastic things that happen in the environment. And just to get a sense, I mean, you can think of it, for an example, if you go back in time, think about a hunter-gatherer economy. Obviously, people's well-being is highly coupled to change the environment, and that's a very different experience from the economy that you and I participate in today. So over time, sort of the economy as a whole seems to be becoming less and less dependent on the environment. This is actually a very profound transition that's been thought about quite deeply by economists in many contexts and thinking about sustainability. And ultimately, the transition is being driven by innovation as we develop different types of human-engineered capital, things like machines, buildings, that are more robust to changes in the environment than sort of things we call natural capital, things like sunlight and rocks and trees, right? And so as we make this transition from depending less on natural capital, more on human capital, there is a notion that the environment should matter less. But empirically, we don't actually know how far we've gotten, right? So the question of this paper is, how far has this transition process taken us? Have we reached sort of escape velocity where we no longer are dependent on the environment at all? Or are we still in some regime where there's some partial dependence, in which case we want to think about how we manage the environment as kind of an economic asset. And so this matters for what seems like an idiotic statement, but I assure you it's actually somewhat profound, okay, if you think about it for a little bit of time. So every day, billions of people are exposed to temperature, okay? Now, it seems silly, but we actually have very little sense for whether or not this is an economically meaningful statement, whether this has any real-world implication for the economy. There's recent work, most notably the Del Jones and Olkin paper, that suggests that poor countries are almost definitely economically impacted by temperature. In fact, they think that high temperatures seem to lower economic output in poor countries. And so that seems to be quite important if you live in a poor country. But from global management, if we think about sort of global climate type problems, the global economy is dominated by rich countries. And so even if you sort of remove all poor countries from accounting, that still doesn't have a massive effect on sort of global economic output. So if temperature actually continues to affect rich countries, then something like climate change might disturb a much larger fraction of the global economy than we sort of previously thought, okay? Because that's the engine driving growth globally. Now, lots of smart people have thought about this, and this is sort of an interesting quote. You know, if we're really rich, there's been a standard intuition that maybe we somehow have the resources to adapt, the sophistication to sort of avoid a lot of these types of environmental impacts. So Thomas Schelling, who won the Nobel Prize, sort of in a very early assessment, when he just sort of sat back in an armchair and thought about what might happen in climate change, under climate change, she said, I conclude that the United States and probably Japan, Western Europe, and other developed countries, the impact of climate change on output will be negligible and unlikely to be noticed. Okay? So there's this general notion that this dimension of the environment may not be terribly economically important. Now that stands in kind of direct contrast to very simple and sort of personal experience that I think we all are familiar with. So in this is sort of one of a funny and interesting study. So Charles Mackworth was a researcher for the British military. And so at the impetus of the Navy, he in 1947 wrote a series of papers studying human performance when exposed to high temperature. Okay, so he has this setup where there's an individual and they're put at a table and they basically have to do arm curls, okay, until they collapse. And the question is, how many arm curls can they do if we turn up the thermostat on the room they're sitting in? Okay, and his motivation. So the answer to the question is this graph on the right that he produced. And so you see on the x-axis is temperature, and on the y-axis, that line coming down is sort of the percent of performance, the number of arm curls till collapse as a function of temperature in the lab. Okay? And so what you see is there's sort of like a general decline in performance, such that at high temperatures, performance is now like 60% of what it was at more optimal temperatures. You can keep that image in your mind, because I'm going to show you some other graphs that end up looking quite a bit like that. His motivation kind of comes directly from, interestingly, it's almost a perfect counter to what Schelling was saying. He says, it's often stated or implied, difficult conditions do not matter, because if we get the incentives right, men will be able to rise above the difficulties of working in hot and humid environments, and so they can satisfactorily complete their allotted tasks. Okay, so we have these two different viewpoints. One in which we think, well, the incentives are the thing that matter, and another in which, it looks like the environment seems to directly matter. And interestingly, in this particular experiment, what he was manipulating was whether or not the incentives matter. Okay, so in one experiment, he tells people how well they're doing and tries to encourage them, and in the other one, he just lets them go. Turns out, under both conditions, you get essentially the same response. Okay, so he's making this case in the 40s that the incentives don't seem to change sort of this physiological constraint. Okay.
Was there an actual incentive or just information?
It was just information in this particular case, but people have played with these types of experiments a little bit. Now, thinking about going outside of the laboratory condition, people have thought about this question quite a bit. So this is a graph of cross-sectional variation across pixels in the world. So William Nordhaus did a really important study where he tries to estimate economic production over a grid of the planet, and then basically for every temperature bin right here, he's just showing the distribution of grid level productivity. It's like a GDP measure as a function of temperature. Okay, and so what you see is that in the grid cells that are getting warmer and warmer, productivity is declining, and there might be some sort of break in the trend around here. Now this is a cross-sectional comparison. Grid cells located in Nigeria are very different from grid cells located in Kansas for a variety of reasons unrelated to temperature. So we don't want to think that this is causal, but many people have wondered whether or not it's going to be causal. And it seems important because if it is causal, it certainly should affect how we think about different types of economic development programs, for example, or how we design policy. Okay, so this is a different motivation, thinking about the geographic distribution of productivity. And then one thing that motivates me in a lot of contexts is thinking about climate change management. So the fundamental problem of climate change is trying to balance the costs and the benefits of any sort of policy, where policy is made up of some emission schedule and some schedule of different types of adaptive investments. Okay, so we frequently write it down as trying to just maximize the benefits versus the cost, and we characterize the benefits of mitigating climate change as some sort of damages that are averted. Okay, so there's very frequently something we call a damage function, which is just a stylized description of economic costs as some function of emissions or global mean temperature. And then stylistically, you can think of if people are adapting and somehow avoiding those damages through investments theta, that reduces the damage. So here, if theta goes to 1, this term goes to 0, and so damages go to 0. Okay, so the idea is if we fully adapt, it doesn't matter what the temperature is doing, our economic performance is going to be invariant in temperature. Okay? Now, to date, this damage function has pretty much been assumed, okay, as has sophistication. And so the question of a lot of this work is trying to empirically understand what is the structure of it and what does theta really look like. Now, theta is adaptation, and we have some sense from observing specific activities or sectors that people are adapting, like people are pretty intelligent and sophisticated in what they're doing. So for example, people can switch economic activity. If you have crops that are very temperature sensitive, you might switch to a less temperature sensitive crop. People can innovate, they can develop new crop varieties, they can build air conditioners, they can move around in space. If it becomes too hot in your region or too wet or there's floods or hurricanes, you can move. People invest in defensive, something we're going to call here defensive investments. These are things like seawalls or air conditioning, things that just physically protect you from these types of environmental insults. And often a lot of the costs of climate changes or other types of environmental changes can be traded away. So if I become less productive in one good but more productive in another good, I can just trade with the guy who benefited in the good I stopped producing, right? And so some of the welfare loss can be dealt with that way. And then finally, we have all sorts of mechanisms in society, things that are like transfers or insurance, that help us deal with sort of the welfare implications, although they may not actually reduce the overall impact. But we know that all these things are going around, they've been observed, and an empirical question is how effective are they in aggregate in sort of decoupling our society from environmental change. Here we go. So the point of departure for this paper is basically the observation that in lots of very highly micro-level studies, things like that laboratory experiment, we observe that high temperature has a negative effect on all sorts of the performance of many factors of the economy. Okay, so in this left figure here, what we're showing is these are all previous studies. The effect that basically as temperature rises, maize productivity increases up to a point, and then it crashes. Similarly, and drawing on papers like the Mackworth paper, labor performance does something very similar at a slightly different cut point. And in a recent paper by Graxoven and Nidell, there's a similar effect with labor supply. So we find that on hot temperature days, people actually work fewer hours if they're exposed to outdoor temperatures, like construction workers and farmers and people who manufacture. Okay? So the question is, these are the building blocks of the economy. They're sort of the primitive units on which everything else is building. If they're responding to temperature in this way, do these effects somehow aggregate or interact, or are they just completely mitigated by all those different sophisticated adaptation mechanisms we were just talking about? What does it do in aggregate when you're affecting things at the very bottom in a sophisticated system? Okay? So the precise question of this particular study is asking whether daily temperature is affecting economic productivity in aggregate. And because we think that adaptation might matter and that adaptation should go up when you get rich, we look into the limiting case of the richest society the world has ever seen. Okay? And so we're going to ask, to date, if any human society has decoupled itself from the environment, it should be present in the richest one. So we're going to look and see whether that's true. So I'm going to very briefly tell you sort of a conceptual framework. And if you like math, you can look at the screen. Otherwise, you can just ignore it. I know we don't have all economists in the room. But what we think about is we think about an economy in which sort of there's multiple things people could invest in. Right? You could invest in, for example, a farming technology or a non-farming technology. And we sort of separate those both because traditionally people think farming is very susceptible to the environment, and because it turns out in our data we can separately observe farming. So you can think that people could allocate labor in farming or non-farming. They could invest in money in non-farming or farming capital. And those various factors might respond to temperature. So here, these terms A describe the productivity of a unit of capital or a unit of labor in one sector. And we might think that those are affected by the temperature. Similarly to observing that, so if corn is declining in productivity with high temperature, that would be captured in the fact that capital in the farming sector, your plot of land, is less productive in response to that. Okay? Now, if people are very sophisticated and they see that productivity is declining in one sector but not another, they're going to move their resources from the unproductive sector to the more productive sector. So we can think about that happening. And so they're going to produce across their sector something that's optimal based on the temperatures that they observe. Okay? So they'll produce some optimal supply. And also we might think that demand for various goods and services might change in response to temperature, right? So I remember in New York City, after the first hot day in summer, like the price of air conditioners always goes up by a factor of 2. Now, we think of individuals as being pretty sophisticated, so they're optimizing, and the model in the back of our head is that every day I wake up, I look out the window, I see what the temperature is, I make some decisions about what kind of economic activity I'm going to engage in that day, and then I do it, okay? And so each day I produce something, Q star, and I sell it for price P, okay? And I do it in my 2 different sectors, but I can be pretty sophisticated in which one I'm investing in, and I do that over and over 365 times. And at the end of the day, I've made some amount of money. These are my annual. Okay, so it's a very sort of simple mechanical model, but the agents are pretty intelligent. Now, they can adapt in more than just reallocating factors. We saw from the literature that people do a lot of different things. And so we can also imagine that people make defensive investments. They buy air conditioners, they invest in irrigation, and they do a variety of different actions, which are costly, that come at a cost, but which change how temperature affects productivity. So this is the differential effect of temperature on productivity. It's described by some unknown function h, and we imagine, just like we did with that damage function, that if I invest very heavily in adaptation, I can drive that marginal effect to 0. Okay. So agents might be doing that. They'll come up with whatever is the optimal approach. And then the final thing that they can do is, like we said before, is they can engage in transfers. They can get government assistance, or they can have transfers between households if someone has economic hardship, and we'll call that data talent. Okay? So that the full model of what we think people are doing in the economy is every day they wake up, they observe temperature, they produce some optimal amount in the various sectors in which they participate in, they sell those products to the market, they make some investments in defensive costs. You can think of a firm, if it's really hot and they spend a lot on electricity to air condition their building, they're going to pay additional costs that day. And then there might be some transfers at the end where they're receiving insurance payouts, or maybe the government's giving them money, or they're paying money to the government. And they do that 365 times. Okay? That leads to their annual earnings. The question here is, given this fairly sophisticated environment where people can adapt across lots of different margins, when we change the temperature, does this object change in its size? Okay? So if the partial of y with respect to daily temperature is 0, that suggests that all these actions are very effective at insulating us from the environment. If it's not 0, that suggests that something about the environment still matters, and that despite all of these sort of sophisticated behaviors, we're still having difficulty insulating ourselves. Okay, so briefly, just to recap, all of the effects of temperature enter the economy by just changing sort of the fundamental productivities of the basic units in the economy. Okay, so capital and labor in farming and non-farming might respond to temperature, and people's demand for these things might change. Okay, people might adjust. They might relocate sort of their assets or their investments or their energies, including migrating, for example, and that could reduce these effects. Prices may adjust. So even if I have a shortfall in production, if the price rises enough, I still can make a profit. And then people can invest in sophisticated technologies or engage in transfers. But all of those things are sort of secondary responses to that very fundamental effect on individual factors. Okay? Now, all of these things will be very effective if they come at low cost. But if there are substantial costs involved with these various actions, people may not undertake them, even if they're optimizing, in which case the environment still matters. So to test this kind of idea, we're going to try to look at some empirical data, and the way we do it is, and we try to understand whether or not changes in temperature are really having a 0 or non-zero effect. Okay, so first thing we do is we reconstruct the history of every county's daily temperature. Okay, we're going to go back to 1970, and we're going to try to look at how county-level productivity is responding to these daily fluctuations, and I'll explain to you how we do that in a second. Then we're going to try to infer sort of the causal effect of daily temperature variations. And the way we do it is we look at counties' economic performance before and after their temperature changes a little bit. Okay, so we never compare, for example, Princeton's county, I don't know if that's the name of the county, but we never compare this county to sort of my county over in Berkeley, right? Because there's lots of things that are different, opposite coasts. what we want to do is we want to compare Princeton today to Princeton tomorrow to Princeton the next day, okay? Because the population is not going to be changing very quickly, and the other types of things in the economy that sort of are changing might be changing more gradually than daily temperature. But many of those things can also be accounted for if we start thinking about regional trends and those types of things, which we'll capture in a statistical model. Okay, so you can think about it in the framework of a randomized trial where you have a treatment group and a control group. The treatment group is Princeton on a hot day. The control group is Princeton on that same day of the year, but where it's a little bit colder than it was in previous years. Okay, so we think of those as reasonably comparable units. And in the third step, what we're going to do is we're going to take the results from that second step if we have time, and I'm going to show you some simulations where we ask two different questions. One, we ask, well, what if we could actually control the temperature of the country? How much more productive would we be? And the second step, we're going to think about climate change. And we're going to use some climate change forecasts to think about if the economy has the same response in the future, what would the economic cost look like through this particular pathway that we're going to inspect here. Okay? Now, the central challenge of this particular study is that we want to know the economy's response to daily temperature, but we don't have daily observations of output. Okay, so we do have daily observations of weather, and we have annual observations of output. But if we're clever, we can actually try to back out what is the average daily response using sort of a clever statistical approach. Okay, so just to remind you, the mental model we have is a model in which every day we wake up, we look out the window, we observe the temperature, we optimally engage in some economic activity, and produce output, and then collect and put all our money in the piggy bank. And then at the end of the year, we, the econometrician, observe why. Okay? And the question is, what does this thing look like with response to it? Now, I'll show you exactly why. There's been some prior work on this, but what we can do is we can do a regression on the count of days at each temperature, and that is actually sufficient to identify the shape of this function with response to temperature. So I'm going to show you why. And I'm actually, because this is kind of important and also not intuitive to everyone, I'm going to show you why 3 different ways of increasing complexity fairly quickly, and hopefully it will develop some intuition for you for sort of why this works. Okay? So in the first example, so how is it that we can get a daily income when we don't observe daily income? Okay? So the first example is imagine that the year is composed of only 2 days instead of many, and that there's actually only 2 temperatures that those days can take on. Okay? So a day can be either hot or it can be cold, and on a hot day we earn $1, on a cold day we earn $2. Okay? So if 2 days of the year that we observe are both hot, then we only earn $2 because we just have 2 days of hot income. Okay? If both days are cold, we earn $4 because we have 2 days of cold day income, which is higher. And if we have a mixture, if we have 1 hot day and 1 cold day, we have $3 of income. Okay? So everyone in this room can easily see, right? We have 3 linear equations, 2 unknowns. So as long as we observe at least 2 different days that are of different temperature, we can infer sort of what the production function. We can back out what y hot and y cold are. Right? This can be just easily solved. Clear? Yes. Okay. Now let's go to a slightly more sophisticated example. Imagine we observe income on the weekly basis, okay, or the year has 7 days in, and that there's a continuum of 10 different temperatures you can take on. Okay. So over here, these are the 10 different temperature bins you might have. This column of numbers is the number of days at each temperature. And over on the right, we're going to keep track of how much money we've earned over the course of the week. Okay? Now we imagine that there is some function describing the productivity of the economy. That's some function of temperature. We're going to call it G, but we don't know what it looks like. Okay? This is what it really looks like, but as we're not observing it. Okay? And what this function does is for a given day, a given temperature, we can go to that temperature, observe productivity, and put that much money in the piggy. Okay, so we have 1 day, it's pretty cold, it's pretty high productivity, and we have some earnings that go into the piggy bank. We have another day that's a little bit warmer, it's actually more productive, and so we have slightly larger earnings on that day. And we continue counting days forward, where we have a couple hot days, they have lower productivity, and at the end of the week, the gray bar is what is actually observed in the data. Okay? We don't observe all those little colored components. Our goal is to back out how big they are, based on the fact that we saw that gray bar, and that we can count the number of days in each day. Now, like you saw before, we had like 2 unknowns. Here we have basically 10 unknowns. Okay?
So we need a large mixture of days, but for example, here on the left, you have 1 week when you have several hot days. And so at the end of the week, income's not that high. Whereas on a different week, we have fewer hot days and more cool days, using sort of that response function I was showing you. So at the end of the week, we have a higher income. Okay? So if we observe enough variations of different distributions of temperature for different weeks, we can back out what is the implied shape of that productivity function. Okay? Because this is what, sorry, that's what it is. Now, I'm not going to stress this because this is a shorter talk, but in the paper, we basically derive the approach of implementing this for a very large number of days, 365 days, with a continuum of temperatures. And the key trick is that there's some unknown productivity function, okay, and we discretize it. So we're not actually going to try to model this as a smooth function. We're going to create a bunch of bins, and we're going to say, you know, if the temperature is in the mth bin, which we index as omega m, we're going to add 1 to like the number of days for that county in that bin. And if we do a regression, just ignore the slide. If we do a regression on the number of days in each one of those bins, we recover the shape of that productivity function. Okay? And that's derived in the paper. So we take that sort of model very seriously, and we end up with this longitudinal data set. We run a regression that basically looks at log income, okay, in county I in year T, and it's a linear function of the distribution, count of temperatures across the full spectrum in year T, the count of temperatures last year, because we might think that if you were more productive or less productive last year, that might affect you this year. We do the same thing for precipitation. I'm not going to show you precipitation because it's pretty uninteresting, not much happens. And then importantly, we're going to have something in here called a county fixed effect, which is basically a county level constant term. So if some counties are just more productive for some unobserved reason, say that people are highly educated and very productive, or maybe it has great geographic attributes, all of that will be observed non-parametrically by this county fixed effect. We'll have a year fixed effect, which is basically a year-specific constant. So if the economy of the country as a whole is very productive, everyone becomes more productive, we're not going to worry about that. So if there's like a business cycle that's correlated with temperatures, that shouldn't be driving our results. And then we're also going to have something here which is a lagged dependent variable. So log of income last year is going to be allowed to affect log of income this year. Okay? And so we're going to estimate also rho, which is an autocorrelation coefficient. Okay? And this is important because a lot of things that change within a county, you can imagine, like if we invest in a bridge 1 year, it's going to make us more productive in that year, and it's also going to persist into the next period and make us more productive in later years. We can actually pull that part of the model out, and it doesn't really change the results, but it really helps clean up some of the noise. Okay. So the thing that we're going to focus on is this term, because these betas are going to tell us what is the shape of that productivity function. We're really interested. Now, I just want to be really clear, sort of, what is the variation in like an X variable, right? That's going to be generating the change in the Y variable. So those county-specific fixed effects are going to absorb any average response or any average variable, actually, in any county. And so if we were to look at, this is actual data from Middlesex County. This is the average distribution of days across temperatures. Okay, so it's bimodal because there's a lot of, this is the county that Cambridge is in. There's summer and winter. And this is the average distribution, okay? So this average distribution and any effect it has on the economy is actually going to be captured by those county fixed effects, okay? These county-specific averages. The thing that drives the model is the fact that in some years, well actually in all years, we don't achieve that exact distribution. So this is the distribution that occurred in Middlesex in 2010. And what you can see is that in some temperature bands, so around 45 degrees, there were many more days. And then at higher temperatures, there were fewer days, for example. Okay? And so it's these small differences, small deviations in the change of the distribution that are going to let us know how much more or less income we can attribute to each one of these bins. Okay? And so in a sense, we're really capturing, like, when we think about climate, there's this kind of, I don't know if you guys follow this literature, but there's a debate about are we observing weather or are we observing climate? Okay? In that debate, I think there are two components of the climate that we care about. And in this paper, we're handling one of them nicely and one of them not so nicely. So the two dimensions of the climate that differ from weather are that one, climate is an expected probability distribution. Actually, it's both of them. So one, it's expected, and two, it's a probability distribution. Here, the changes are unexpected, but we are modeling the full response to the full probability, the full distribution of temperatures, okay? So it's not just sort of a shift in average temperature at the county level, it's a small distortion in the distribution of what the daily temperatures actually are, and we're actually picking that up, okay? So we're getting halfway to really measuring the climate, even though we are identifying all of these changes off of random fluctuations. Okay, I won't get into detail, but basically we pull county level data from the US government, and it's put together by reports from employers. So it's not like people can really change what they're reporting to the government kind of based on what the economy is doing. The employers always have to report these numbers to comply with federal law, okay? And so we think that these reports are pretty exogenous. And we also are able to obtain government transfer data through a Freedom of Information Act, and this lets us look at different types of insurance, so income insurance, and it also lets us look at crop insurance and ad hoc disaster payments to counties from the federal government. So that's going to let us start to peer into the box and see if transfers are having an important effect in mitigating the effects that I'm about to show you. Okay. Are there any questions up to now? You guys are sort of very quiet. You should feel free to interrupt if you're.
I just have a quick question, which is it seems that doing the analysis the way you're doing it, you're getting only adaptations that are possible instantaneously within one day. And any kind of longer term adaptations, there's something this method won't capture.
Exactly. That is correct. And that's what I was saying. When we think about climate, there's these two dimensions. One is that it's the distribution, and one is that it's expected. So it is true that the things that we're observing are sort of short-term coping. It could be the case that some dimensions of cope rooms we capture. Like if I have one day that's really unproductive, I could work really hard in subsequent days to make it up, and we're going to capture that. So if that's happening, we'll see that like a really hot or cold day will have no effect. But if it's some sort of very long-term investment, like building a seawall, because I know that sea level is going to rise very gradually, we're not going to pick that up.
So in this particular case, does this correspond literally to like turning up the air conditioner versus going out and investing in new equipment?
Yes. So this will capture things like the air conditioner, and it will capture. And now, if we think so, another important point is that these counties have been exposed to these temperature distributions for hundreds of years. So if we've adapted optimally, we probably should have already bought a lot of that equipment. In which case, we can just utilize it on these hot days, and there will be no effect. But we're not capturing how people will respond to a future trend, where their expectations are driven. Sure. Yes?
I have a question about the theory you're testing. So the theory basically assumes that temperature enters the productivity term, but there's no response from the labor side. Because I can imagine that if the temperature goes up, and the reservation wage for workers to work can go up, so the opposite effect can happen, that the wage can actually go up instead of go down. So
that's allowed for in principle. So when people are changing how they allocate their factors, one thing they can do is they can reallocate labor towards leisure. So people can, for example, work less. That's definitely in there. Yeah, that's definitely in there, and that's something that we observe even empirically. So we know that's happening. Yeah.
So when you're reconstructing daily income data, you're assigning higher values for colder days. Is that correct?
We're being actually agnostic. We're trying to back out what is the correspondence between daily temperature and income. We don't know it, and that's the whole goal, is trying to recover it from the data. Yeah.
Wait, so that means you allow for lower productivity for colder days too, right? Because climate change makes weather more extreme, not just warmer. So
for sure, that's an empirical question, and we're going to see what cold days versus hot days do. We don't know, and it may be the case that cold days are more productive or less productive. Yeah. Okay, so this is the main result. If you sort of forget everything else from the talk, this is the thing you should remember. Okay, this is a graph of what these coefficients on the daily temperature bins are. So implicitly, what this is the sort of production function of a county with respect to daily temperature. Now the y-axis is in percent of annual income, because that's what we're observing. Okay, so one days of work is like 1 over 365 of your annual income. And so just for sort of calibration, I put this dashed line here, which is 36.5% of a randomly selected day's income, okay, per capita. And so what you see is that there's sort of a peak, a well-formed peak in the middle. So the maximum productivity is occurring around 57, 56 degrees Fahrenheit. At lower temperatures, like you were suggesting, we observe that it's sort of gently declining. And then at these very, very cold temperatures, sort of our estimates kind of go crazy. And as you can see, these gray bars are confidence intervals. So we have very few days that are at these extremely cold temperatures. So we don't really have a good sense of what's happening. But it looks as though it's declining, kind of as one might expect. And then above about 59 degrees, we see productivity at the county level declines. And it declines approximately linearly and fairly steeply. Okay, so it's about 1.5% per degree Celsius. Now, a couple things are worth pointing out. First of all, if you're familiar with sort of the macroeconomic literature, the slope of this response up here is the same slope that we observe at the macroeconomic level in poor countries. Okay, so the sort of derivative of productivity in the US doesn't look that different if we go to the high temperatures. The other thing to point out is that these are daily average temperatures. So they're 24-hour averages. So if you're thinking to yourself, well, 56 degrees sounds pretty cold, a 56-degree day is a day when the temperatures probably go up to about 70. Okay, so a day with a high of 70 is kind of what we're estimating is the productivity, the maximum productivity. Okay. Now, so on these very hot temperature days, we're seeing that income is approaching. It's roughly 30% of a daily, an average day's output. Okay, so a hot day reduces output by about 50%. It's a fairly large effect. So these figures are kind of loaded. So one question is, this is the result I was just showing you, and income has many components, like we were showing in the theory before. So one thing we can look at is just pure earnings. Okay, this is money that you earn and take home. So this is not transfers. This is not any type of other investments. And we actually see that the earnings response has the same structure, and in fact our earnings decline much more steeply than total income. So the other things we're doing are sort of smoothing out this response, but not completely. If temperature didn't matter at all, we would expect people to have a totally flat response, right? The derivative of productivity with respect to temperature would just be 0. So these are the effects of daily temperatures this year on my income at the end of this year. The other thing to look at is what happens in the following years, right? So if we look at the lag, if we look at how last year's temperature affected us, we see that it has almost no effect, okay? So experiencing a hot day 1 year ago doesn't affect our earnings in the current year. This is the estimated response to last year's temperature distribution. It's mostly flat. The only thing we see is that high temperature days, there's kind of an uptick. So if we had a couple of these extremely damaging days last year, we do observe that in future periods, something's happening and people might be working harder or something to make up for it in subsequent periods, but the size of this jump is roughly less than half of what's lost the year before. Okay? But overall, this is pretty flat, and it kind of reassures us that this approach is picking up the thing we're trying to pick up. It's not like it's just temperatures in this year are leading to output this year and not.
Do you have a corresponding graph on the duration or the number of days that you had these extreme events rather than just temperature? So I had one day where it was 85 degrees, it was 34. Not if I had like a whole week or a month of 85.
So okay, I think what you're getting at is that like if you have a very warm spell, for example, that's different. Yeah, so that's very important. And so the approach that we're implementing here is capturing what is the average effect of a day in each one of these bins, unconditional on the distribution of temperatures around that day. Okay, and one reason for that, we're thinking about this because it's an important question, but it's actually much harder to model the response to all possible sequences of days. Okay, because you can imagine, right, if we have about 20 temperature bins, all pairwise combinations of days mean you have 20 times 20 pairs, so the dimensionality of the space goes up exponentially. So it's kind of a harder empirical problem. So we haven't done it. And so basically, if we see that there's an effect of high temperatures days, This is the effect of a randomly selected hot day. And it might capture the effect of some neighboring days also being hot. There's no sort of explicit heat wave effect that we're modeling, but it's embedded in these estimates. Yeah.
Could the uptake, you just described the uptake potentially to working harder in response to the knowledge, whatever, but it could also be extending the capital investment, changing the capital investment schedule.
Yes, it's anything that you're doing to compensate. And so we're observing that in the subsequent year there is some compensation, but only to the very hottest days. And we're observing basically nothing to these more moderate days that still had a decline. Yeah?
I assume that you, for the warmer days, you make some sort of correction for the percentage of the labor force on vacation.
So we think of that as a way in which people might be actually re-optimizing their activity.
Okay.
Right? So if it's true that people are just not working on hot days because it's not productive, that's just one adaptation response, but that's important for us to know. Right? Because like if we have more hot days, for example, people might readjust their labor schedule because they might want to change how hard they work. That was the exact point that was made earlier about allocating between labor and leisure. That's a very important. Okay, so one of the reasons, one of the motivating features for me was that I was pointing out at the beginning was to think about adaptation. Okay, so we can look at a rich country and ask whether or not the population is adapted. One way we can also think about it is, okay, in this rich country, have people learned over time? So we actually have 40 years of data. So we can look decade by decade to see what the response is. Okay, and these are the responses when we estimate each decade separately. And so the first point is that largely they look the same. Okay, there doesn't look like there's been any sort of change in our overall economic sensitivity to temperature. And in fact, if we just look in the 21st century, okay, in the richest country in the world, we still see this decline that's approximately linear at high temperatures. So we think there hasn't been any sort of, this is evidence that there's not a tremendous amount of new uptake of new technology or new investment. The other thing we can do is we can look across the country. So we can look at the parts of the country that are hot, and we can look at the parts of the country that are cooler, and we can ask whether or not the people who are more used to this type of high temperature day have a different response. And so what I'm showing you here is a breakdown by 4 different regions, and the dashed black line is showing you the pooled estimate for the whole country as a whole, the thing that I've been showing you up to now. Okay? And so what you see, for example, is that the Northeast largely reflects the pooled response, as does the West. Now, if you look at the South is a place that's very hot. So if we think that people might be investing in more air conditioners, for example, to insulate themselves, we'd expect the derivative to be closer to 0. And if anything, so the black line, if you squint, this derivative looks like it might be a little bit less steep than the national average. So that seems consistent with this notion of how people should be adapting. Although importantly, this difference is not statistically different. Okay, so we can't reject the null hypothesis that sort of the South behaves just like everyone else does. And also, some of this difference looks like it might be driven by noise in the estimated constant. So if you imagine just translating this graph down a little bit, because it looks like it's been boosted up, perhaps due to noise, then we actually look just a lot more like the national average. So it could be, there's various types of sampling that are coming into play. And if you look at the Midwest, you see that the response actually looks a little bit steeper than the national average. And I'll show you in a minute, it looks like that's being generated by the fact that agriculture is especially sensitive to temperature and seems like it's more difficult to adapt. So this also suggests to us that this is not inconsistent with there being some adaptation, but it is far from providing sort of overwhelming evidence that there's really effective adaptation, at least in cross-section across the US. Yeah.
Is it just a function of how you construct the y-axis that in all cases 55 degrees is the 0 point, or is there some information?
Yeah, so 55, so when you do this type of model, you have to pick some temperature to be your benchmark temperature. And so by construction, everything is relative to that, which is part of what the issue I'm highlighting here is, because basically if the effect at 55 is kind of not known very well, it can cause the graph to be translated up or down. Okay, so then another thing that we can think about is, well, we can have these hot temperature days, and if they're really affecting economic production, if we have a hot day, whether or not it falls on a weekday or a weekend is pretty random, right? We don't think that those two things should be affected. So we can actually describe, instead of one productivity function, G, we can have two of them, where annual production is sort of the sum of all earnings I make on weekdays and weekends, and those two things can respond to temperature separately. So on the left is what we estimate the response is to hot weekdays, and on the right is the effect of weekends. Okay, so on the left, it pretty much looks like what we were showing before, with all the different factors being more or less uniformly productive, or for high temperatures, for low temperatures, and then at high temperatures, productivity declines. If we look at weekends, if anything, it looks like it might be gently sloping upward. Now, we think, we can't observe in everything we would like in this data, but what we think might be happening is that many of the sort of economic activities that we engage in on the weekends are actually complements of high temperature, right? So like we like to go shopping, we like to eat at outdoor cafes, so it's quite possible that we sort of are doing a lot more things that are beneficial to the economy when it's warm on weekends, but on weekdays, those same temperatures have an adverse effect because we're trying to do things that are less sort of consumption activities and much more strenuous maybe or productive. Okay, so we think that this is pretty compelling evidence that something is pretty important going on. We can also try to drill down and understand what are the underlying mechanisms. So the theory I wrote down for you in the beginning was saying that there's some basic factors of production that are responding to temperature. So in previous work, Wolfram Schrenker and Michael Roberts sort of showed, and this is related to the graph I showed you before, that various crops in US counties that are modeled very similar to what we're doing here respond to daily temperature in this highly nonlinear way, with a kink occurring around 29 degrees Celsius. Okay? We can actually observe county level income attributable just to crops. And when we replicate our approach on just that subset of income, we recover this response function, which is, in the paper we go through in great detail, sort of comparing the breakpoints and the magnitude, and it's almost an exact reflection. And so what that tells us is that whatever is happening sort of in particular, tells us that prices, so we've often thought that if people have low output, they're compensated for having higher prices. What we're seeing is that when quantities are declined because of high temperatures, the prices don't compensate, okay? At least not enough to offset the losses. And basically, yield losses translate directly into income losses at the county level. And we can also look at total farm income. Now, this response has obviously a kink that's at lower temperatures. So that might be because the farmers are doing other things on their farm to compensate for sort of yield losses. But it might also be the fact that there's human labor on the farm, there's machinery on the farm, there's livestock on the farm. There's many other things unrelated to crops that could be responding to temperature. So we don't know exactly what's going on, but we think together these both sort of very strongly point to these types of mechanisms, okay? Because of the structure of the response is so complicated. Yeah?
So I wonder if the US might actually act a bit more like a middle income or a poor country because of the huge amount of income inequality. So for example, there are a huge number of migrant workers in the southern states, and they might be more sensitive to temperature fluctuations, and that might sort of distort, it might sort of make it look like a rich country would be more sensitive to temperature than it actually would if you look at something like Germany or Canada, where there's just less income inequality.
That's definitely a possibility. To the extent that we think that like the Northeast is less susceptible to whatever we want to call that, having more exposed labor. We saw the same response in the Northeast, but it is true we can't break it down. We could look sort of by demographic composition, but it's going to look largely like the cross-sectional result I showed you when we looked at the different regions. So to the extent that that can be dealt with there, that's handled, but I'm completely open to that. We also made the point that it might also be things that are non-crop related, right? Like we saw the individual workers were working less hard, and we observed that people supply less labor on hot temperature days. So this is the Grafton and Nidell result looking at labor supply. And what you see for people that are exposed to outdoor temperatures is that they basically provide roughly the same amount of labor, except when it becomes hot, and then it declines, but more gradually and sort of less sharply than the yield response was. And we can look at non-farm income at the county level, and we recover a response that looks both, it has a very similar breakpoint, and it's also got a similar level of noise. But overall, there's a decline in non-farm income for all temperature bins above our threshold, except this very last bin. So this very last bin is kind of, there's a lot of uncertainty. We can't exclude the fact that it looks like the bin right before it, but it kind of makes this graph visually less appealing. But overall, we find that the structure of the response is quite comparable and seems consistent with this type of mechanism, something like a labor response. The quality of labor response, like the guy doing arm curls, is structurally similar here, but it's roughly 4 times larger, and that seems to be consistent with the size of the effect that we estimate. So that's sort of compared in the paper. Finally, we can also think about transfers, right? The government compensates for a lot of these losses by moving money around the country, trying to make people better off. And so one thing we can look at is if you have a lot of hot temperature days that are reducing your income, does the government give you money to compensate for that? So that's this top graph, and what we see is that there is no effect of temperature on government transfers. And in fact, it's a very small confidence interval. The y-axis here is the same as the one I've been showing you before, so we can say with great confidence that there's almost no effect. And we can also, people have thought about the fact, have pointed out that on high temperature days you have a lot of health-related issues, as you do with cold-related days. So we can look specifically at public medical benefits, and it's much noisier, but it looks like there's no change in transfers to the county, right? There's no clear evidence of the response we would expect. The only place where we see clear response is when we look at crop insurance payouts. And we actually see that when you have a sequence of those very high temperature days that are similar to the ones that are most economically damaging for crop insurance, for crop income, we see that there is compensation through federal crop insurance, but the size of this effect is roughly half of the losses that we observe, and it's actually all captured in the income losses. So if this wasn't happening, our earlier results would just be larger, okay? But there is some adjustment that some transfers that are happening. We have only a few minutes left, so I want to talk really quickly about these 2 thought experiments, because I think they're kind of interesting. What we do is we take this result about what we think the productivity response to temperature is, and we do two questions that help us think about these magnitudes. So the first one is to ask, like, what if, in economics we do a lot of optimization. We think that people sort of choose the optimal amount of labor or the optimal amount of capital. What if they could also choose the optimal temperature? Okay? So every day, imagine that the mayor of your county wakes up and he sets the temperature to maximize productivity in the county. Okay? It's kind of like a silly thought experiment, but it kind of helps us get some sort of sense of the magnitudes. How much pressure is the distribution of temperature today exerting on the US economy? Okay? And then we're going to simulate a counterfactual where counties are actually exposed to the real temperature that they were actually exposed to. Okay? So to give you a sense, these are what those 2 temperature distributions look like. Okay? The mayor of each county is going to optimize, he's going to set the temperature to 56 degrees every day. And so that's going to lead to a temperature distribution where there's a ton of stacking at that temperature. Okay? And that's going to be compared against the historical actual distribution of temperature, which is the orange line. When we do simulations, this is the result. Okay? So we see that basically the historical simulation tracks observed income trajectory very closely, but when we allow for counties to optimize their temperature, we have much more rapid economic growth. And on net, it looks like sort of the randomness of daily temperature, our inability to control the temperature, could be attributed with a burden of 1.5 percentage points of growth. Now, of course, this is a back of the envelope estimate, but it suggests that this is a sizable effect. Mike is standing up here, so the last number I'm going to leave you with is we can do the same thing but zoom to the end of the century and ask, okay, if we look at climate change and project it onto the country, what is going to happen? These are the projections, and these are the growth rate penalties. Okay, so we basically, there's a distribution from a bunch of different climate models, but the mean estimate is roughly a decline of income growth of about 0.12 percentage points per year at end of century if we just subject the country to those distributions. So I'm going to stop talking and leave these on the screen. But the main point is that wealth, the sort of qualitative stylized fact to take home is that wealth alone does not look like it is sufficient to completely decouple the economy from local environment.
Let's thank Saul first. We have about 5 minutes. Take your real quick.
Go ahead.
Hey, just curious, can you look at the actual economic growth rates in a place like San Diego or central Kenya or something where they have nice constant temperatures year round and see, is there any way to back out to see if those actually have higher growth rates on average than the more variable?
You mean in a cross-sectional?
Yeah.
So, you mean within the U.S. or across countries?
Anywhere. If temperature is having that kind of effect on.
So globally, the response looks similar. Actually, it's funny, I have some extra slides not for this talk, but in another paper with these guys, we do the same things with macroeconomic data. Okay? And so we compare countries around the world, and we basically recover a response that looks just like this black line. And so what you're saying are countries like Kenya and Nigeria that are very high temperature countries, and the slope of this function is almost the same as the slope that we're covering within counties. So we just compare counties.
So I guess what I'm asking is like a place that has fairly constant temperatures around the year over time, like San Diego, California, or Kenya actually, which has places that are very sort of constant over the year. Can you see that they have higher growth rates on average in places that have more variable temperatures?
So the prediction is not necessarily that that's true. If they're a very stable temperature, it depends on what that temperature is, on what effect it would have on the economy. Because you could have a very stable but bad temperature, right? That's like what Nigeria has. But the other thing is that we don't like to do those comparisons because there's lots of things that are different between San Diego and other locations around the country. So even if we look at San Diego, we don't have like a comparable control group. So we can look at the average growth rate in San Diego, and we can imagine there's a component due to the temperature, and there's a component due to everything else, but we can't separate those two out. And that's like, we want to know that thing, but we just can't know that thing reliably. So that's like the central frustration. Yeah.
In the very last point that you made about the 0.12% penalty for the long-term future, was that a response to the projections of global average temperature change, or is it a more explicitly simulated frequency of extreme events above a particular temperature threshold condition?
So it's actually a pretty sophisticated simulation. We actually take a full probability distribution for every county of what it might experience in the future based on 40 climate models. So each county is subjected to a different distribution with some covariance with other counties. So it's sort of accounting for the extreme temperature events, but importantly, it doesn't account for things like hurricanes. Okay, this is just direct temperature exposure. So if there's drought and hurricanes and other things that matter, that's added on top of that.
One more question.
So you had said early on that you looked at precipitation, but didn't find anything. Is there anything interesting at all with precipitation, or is it really just completely?
Well, so we don't see sort of a clear response to precipitation, but what we think is that probably the reason we don't, it's not that precipitation doesn't matter, but the distribution of precipitation may not matter so much. So the thing is that water is very easy to store between days. Temperature is much more difficult to store between days. So daily temperature matters sort of affects you instantaneously, but I can smooth out water over time. But there's still probably big important effects of trends, for example, but we just can't measure those here using this approach. So, yeah.
So let's thank Saul for a very thoughtful. Are you going to hang around?
Yeah.
If anybody wants to talk to him.